Welcome to Cambridge IGCSE Physics, Lesson 23.1, Basic Thermal Applications. Today we explore how heat transfer principles apply in everyday situations. We'll examine conduction, convection, and radiation in practical contexts like kitchen pans and room heating systems. These applications demonstrate the fundamental physics principles governing thermal energy transfer in our daily lives. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, explain applications of conduction, convection, and radiation in real-world contexts. Second, understand heating kitchen pans through conduction processes. Third, understand heating rooms by convection currents. These objectives align with Cambridge IGCSE assessment objectives. AO1 tests your knowledge of thermal concepts, AO2 examines your application skills, and AO3 evaluates your analytical abilities. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, thermal applications, which means practical uses of heat transfer principles in everyday situations. Second, conduction, which means heat transfer through direct contact between particles without the particles themselves moving. Third, convection, which means heat transfer by fluid movement creating currents that carry thermal energy. Understanding these terms precisely is crucial. Remember to use SI units, temperature in Kelvin or degrees Celsius. Let's explore conduction in kitchen pans. The fundamental principle states that heat transfers through solid materials by particle vibration. Energetic particles vibrate more, transferring kinetic energy to neighboring particles. Pan design demonstrates this principle. The metal base is a good thermal conductor, allowing efficient heat transfer from the heat source. The plastic handle is a poor thermal conductor, acting as an insulator to protect hands. The thick base ensures even heat distribution across the cooking surface. The process follows this sequence. Heat source transfers energy to the metal base, which conducts heat through to the food contents. The diagram illustrates heat arrows entering the metal base and conducting upward to the food. Now we examine convection in room heating. The convection process involves fluid movement transferring thermal energy. Unlike conduction, the particles themselves move, carrying energy with them. Radiator operation follows this sequence. First, the radiator heats air near its surface. Second, warm air rises because it becomes less dense when heated. Third, cool air sinks because it is more dense. Fourth, this creates circulation currents throughout the room. The result is uniform room temperature distribution. The diagram shows red arrows representing warm air rising and blue arrows showing cool air sinking, creating a continuous circulation pattern. Thermal radiation transfers energy by electromagnetic waves without requiring a medium. Unlike conduction and convection, radiation works through empty space. Common applications include first, solar heating, where the sun's radiation travels through space to warm Earth's surface. Second, infrared heaters provide direct heating without air movement. Third, thermal imaging detects heat signatures for medical and security purposes. Fourth, cooking grills use radiant heat to cook food directly. Key properties of radiation. It works through vacuum because no particles are needed, travels at the speed of light, which is 3.0 times 10 to the power 8 meters per second, and all objects emit thermal radiation depending on their temperature. Let's work through an example about pan heating. The problem asks, explain why pan handles are made from plastic. We analyze this systematically. First, identify the heat transfer method. Heat conducts from the hot pan base through the material. Second, compare material properties. Metal is a good thermal conductor, allowing heat to flow easily. Plastic is a poor thermal conductor, blocking heat flow. Third, explain safety considerations. If handles were metal, they would become dangerously hot. Fourth, state practical benefits. Plastic handles remain cool, preventing burns. The answer is, plastic is a thermal insulator preventing burns by blocking heat conduction from the hot pan to the user's hand. This example compares heating efficiency between radiator positions. The problem asks, compare heating efficiency of radiators at floor level versus ceiling level. We analyze both scenarios. Floor-level radiators work efficiently because warm air rises naturally, creating strong convection currents. Cool air sinks to replace the warm air, maintaining continuous circulation. This provides efficient heat distribution throughout the room. Ceiling-level radiators work poorly because warm air has nowhere to rise, reducing convection effectiveness. Heat accumulates near the ceiling, providing poor distribution to the occupied space below. This is less efficient for heating where people actually are. The conclusion is that floor-level radiators are more efficient due to natural convection patterns working with gravity. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, name the 3 methods of heat transfer. This tests your fundamental knowledge of thermal physics. Question 2 is intermediate. It states, explain why car radiators have fins. This requires you to apply heat transfer principles to automotive engineering. Question 3 is advanced. The question is, design an efficient room heating system using all 3 heat transfer methods. This tests your analytical and design skills. For all questions, remember to use scientific terminology correctly, explain the underlying mechanisms clearly, and consider practical applications. Write your answers now before looking at the solutions. Physics principles power our modern world. Let's see how today's concepts apply in practice. In building design, insulation materials reduce unwanted heat transfer, improving energy efficiency and comfort. Engineers select materials based on their thermal conductivity properties. In electronics, heat sinks conduct heat away from computer processors, preventing overheating and component failure. The fins increase surface area for better heat dissipation. In meteorology, convection currents in the atmosphere create weather patterns, with warm air rising and cool air sinking on a global scale. Career-wise, thermal engineering designs efficient heating systems, HVAC, heating, ventilation, and air conditioning. Engineers optimize building climate control, and renewable energy specialists develop solar thermal systems. Future technology includes smart thermostats using thermal sensors, efficient heat pumps for sustainable heating, and thermal storage systems for energy management. Let's review the solutions. For question 1, the answer is conduction, convection, and radiation. These are the 3 fundamental methods of thermal energy transfer. For question 2, fins increase surface area for better heat transfer. Heat conducts from the engine through the metal fins to the surrounding air. Then convection carries the heated air away, cooling the engine. For question 3, an efficient system combines floor radiators using convection currents, insulated walls reducing unwanted conduction, and radiant panels providing direct radiation heating. Exam success tips. First, identify the heat transfer method before explaining the process. Second, explain particle behavior. In conduction, particles vibrate. In convection, particles move. Third, remember radiation needs no medium and works through vacuum. Fourth, use specific examples to illustrate principles clearly. Let's summarize today's lesson. The key points to remember are, first, conduction transfers heat through solids by particle vibration. Energetic particles transfer kinetic energy to neighboring particles without the particles themselves moving from place to place. Second, convection transfers heat by fluid movement creating currents. The fluid particles themselves move, carrying thermal energy with them. Third, applications include kitchen pans using conduction through metal bases, room heating using convection currents, and thermal design in buildings and electronics. For further study, practice identifying heat transfer methods in everyday situations. Analyze thermal applications around you, from cooking equipment to heating systems. Prepare for thermal calculations involving heat capacity and energy transfer rates. The next lesson covers quantitative thermal calculations, building on today's qualitative understanding of heat transfer mechanisms.